Hi, welcome to the 10th lecture of General Chemistry. Today we'll be talking about acid-base chemistry. And I think the title slide might seem appropriate to any of you that have done titrations in lab. You know how hard it is sometimes to get that equivalence point just right. So hopefully this doesn't happen to you in this quarter in lab. All right, last time we went through the start of Chapter 4. Chapter 4.1, we talked about water, definition of solvent and a solute. We talked about solution chemistry, certain properties water has that makes it a good solvent. And then we talked about the common units for solution questions. We moved on to Chapter 4.2, which was dealing with ionic reactions, writing ionic equations, and we defined what electrolytes were. Now, 4.3 was precipitation reactions. We talked about general solubility rules, and we saw that you can use ionic equations in precipitation reactions. And today you'll see that you can actually use ionic equations in acid and base reactions as well. Okay, so to start off today, I'd like to do a few review questions. Here's the first review question. It's dealing with HCl, strong acid. And the question's asking how many milliliters of a commercial HCl stock, which is at 12 molar, do you need to prepare 240 milliliters of 0.1 molar HCl? So take a few minutes here and try answering this question. It should be fairly simple. Okay, so let's work through this. If you remember, these important equations, M1 V1 equals M2 V2. You can also think of this as C1 V1 equals C2 V2 because the M stands in this equation stands for molarity. So if you wanted to think about that as a concentration instead, that would be a good way to think about it. Because you can have concentration expressed in different units than molarity. So it really doesn't have to be molarity. But in this case, in this example, we're dealing with molarity. So thinking of it as M1 V1 equals M2 V2 is appropriate. Okay. So we know what equation to use. How do we set this up? Right? You have to define 1 and 2. So let's define 1 as the initial stock solution and 2 as what we want to prepare. All right, now reading through the problem, we're given the M1, the concentration of the stock. We're given M2, the concentration we want to get. And we're given V2, the volume we want to get. What we're asked to find is V1. So we can rearrange this equation. V1 equals M2 V2 over M1. Now we can plug in numbers. V1 will equal 0.1 molar times 240 milliliters divided by 12 molar. See that the molars cancel out. We're going to be left with an answer that's in milliliters, and we get 2 milliliters. If you notice, all 4 of our choices are in liters, so we have to convert milliliters to liters. There's 1,000 milliliters for 1 liter. So the milliliters would cancel. 2 divided by 1,000, that's 2 times 10 to the minus 3. The answer is B. Okay. Let's try another question. If 3.423 grams of aluminum sulfate are present in 1 times 10 to the second milliliters of solution, what is the sulfate ion concentration? So pause the lecture and take a few minutes, try to answer this question, and then we'll go through it. Okay. So what is the first step here? We're given a mass of aluminum, and we want to find a concentration of sulfate ion. So we're given mass. First step would be to convert into moles. How do you do that? Well, you take the mass, divide that by the molecular weight, and what you're left with is 0.01 moles. Okay, that was pretty simple. Now you know the volume as well. The volume is 100 milliliters. So 0.01 mole divided by 100 milliliters. But all the answers are in molarity, so we'd want to get it in moles per liter. So to do that, we times it by a conversion factor, again 1,000 milliliters per 1 liter. What we get out is 0.1 moles per liter. It's important to remember that this is referring to moles of aluminum sulfate. Sorry, that's a 3. So this is not quite the answer yet, because remember it's asking for sulfate ion concentration, not aluminum sulfate. So we know we have 0.1 mole per liter aluminum sulfate. How many moles of sulfate ion? And you can just tell that by the chemical formula, this coefficient. So for every 1 mole of aluminum sulfate, there are 3 moles of sulfate ion. Remember, this is a strong electrolyte. It dissociates completely. So the answer would be 3 times this. You can also think of it as 0.1 moles per liter Al2SO43 times the conversion factor 3 moles sulfate ion for every 1 mole of aluminum sulfate. Sorry, and I kind of ran out of room there, but so the correct answer is C. Okay, finally, third review question. This is more conceptual. Predict the identity of the precipitate formed when solutions of sodium carbonate and calcium chloride are mixed. To do this, you take the positive ion from one of the compounds and you add it to the negative ion of the other compound. So sodium plus chlorine. That sodium chloride, we know that that is soluble. Okay, that's table salt. Let's try it again for the other combination. So we have calcium plus carbonate calcium carbonate. And if you remember, calcium carbonate is insoluble. So that would be the answer. All right. Let's get on to new material. So today we're going to be talking about starting with chapter 4.4. It's a basic overview of acid-base reactions and titrations. Then we're going to move on to chapter 18, and we're only going to be covering material from 18.1 through 18.3, and I just sort of generally called this acid-base chemistry. In particular, what we'll be dealing with in chapter 18 is the dissociation constant, Ka, for weak acids. Weak acids, their relative strengths to one another. We're going to learn how to calculate pH. That's important. And then we're also going to talk about the Bronsted-Lowry definition of acids and bases, and the idea of a conjugate acid-base pair. So let's start with 4.4. The first definition of acid and bases would be the Arrhenius definition. It basically tells you what an acid or a base does in water. So the Arrhenius definition of an acid is any substance with hydrogen in its formula. When it dissociates in water, it yields H plus in solution. And I'm going to point out here that H plus, you never find H plus in water by itself. You always get H3O plus. This is called the hydronium ion. So H plus is never isolated in water. It's always in the form of hydronium ion. So H plus and H3O plus are equivalent terms when you're talking about acids. So I might call this the acid concentration later on in this lecture. I might also refer to it as H plus concentration or H3O plus concentration. All three of those terms are equivalent. Okay, so that's the definition of an acid as far as the Arrhenius acid-base definition is concerned. So what is the definition of a base? Well, a base is a substance with OH in its formula that dissociates in water to yield OH minus in solution. So when acids and bases react with one another, they undergo what is known as neutralization. And what that reaction is, in general, the generic form of that reaction would be H plus, your generic acid, plus OH minus, generic base. They come together, react, neutralize, and they form H2O, water. In the real world, you need counter ions. The H plus needs a counter ion. The acid in the OH minus needs a positive counter ion. So in real world acids and bases, when they neutralize, it leads to the formation of a salt and of water. And let's see an example of that. With HCl, hydrochloric acid, and NaOH, sodium hydroxide, when they are mixed, they undergo neutralization, and you get a salt, which is sodium chloride, and water. You see that the positive ion in the salt comes from the base, and the negative ion in the salt comes from the acid. Now, how can we write acid and base equations? Well, the first way is the molecular equation. And this is, again, like we talked about last time, the products and the reactants are written as their undissociated molecules. So we'd have HCl, aqueous again, because it's in water, plus NaOH goes to NaCl plus H2O. If you remember from our ionic equations dealing with electrolytes and also the precipitation reactions, we can take the molecular formula and expand it to the total ionic equation. And this shows everything as their dissolved ions. So HCl would become H plus Cl minus. Sodium hydroxide would be Na plus OH minus. You have the salt, Na plus Cl minus, and then H2O is the only molecule in this equation that is not dissociated. Now, if you remember, you can take the total ionic equation and cancel out the spectator ions. So if we have the total ionic equation, you notice that there's certain ions that are the same on both sides, the chloride and the sodium. You can cancel those out, and what you get is a net ionic equation. And you can also refer to this as just the net equation for acid-base neutralization. And that is H plus OH minus goes to H2O. And this is the same for every acid-base reaction. So if you're ever asked to write the net overall equation or the net ionic equation for an acid-base neutralization, it's going to be H plus OH minus goes to H2O. Now, if we look at what are strong acids and strong bases, there's a list here. Your book also gives you a table, which we'll see next slide. The important thing to remember about a strong acid or a strong base is that they're completely ionized in water. So they're strong electrolytes. Let's go through the list. There's HCl, hydrochloric acid, HBr, hydrobromic acid, HI, hydroiodic acid, HNO3, nitric acid, H2SO4, that's sulfuric acid, and then HClO4 is perchloric acid. So there's 6 strong acids. You can assume that any other acid is a weak acid. These are the 6 that we will consider strong. Here's table 4.2 from your book. It's a little bit more complete. Again, there's only 6 strong acids. And you notice you have 3 halogens forming acids with hydrogen, the chlorine, bromine, and iodine. But you see that down here, HF, that's actually a weak acid. So it's something you need to remember, that HF is actually a weak acid. HCl, HBr, and HI are stronger acids. Another important weak acid is phosphoric acid, H3PO4. And another weak acid that you see quite a bit is acetic acid, which is CH3CO2H. We can also look at what are strong bases. We have basically all hydroxides are strong bases. Sodium hydroxide, potassium hydroxide, calcium, strontium, barium. And then an example of a weak base would be ammonia, NH3. So let's try a practice question with strong acids. Let's see, can you remember which ones are strong acids? Let's go through the list. So HCl, hydrochloric acid, that's a strong acid. H3PO4, that's phosphoric acid. If you remember, that was actually a weak acid, so that's not strong. H2SO4 is sulfuric acid. That is a strong acid. HBr, that's another strong acid. CH3COOH, that's acetic acid. That's a weak acid. And HF, that's also weak. If you remember, that is the one exception to the halogens. That is actually a weak acid. So what we're left with for strong acids would be 1, 3, and 4. And that is choice B. Okay, on to question 5. What are the major species present in an aqueous solution of 1 molar HCl? So take a couple minutes here and try to answer this question. Okay. So the important thing on this question is this word major species. Now if we look at HCl, that's a strong acid, so that's going to be completely dissociated. So that will be in the form of H plus Cl minus. Now if you look down here, we don't have the option for H plus, but remember, when H plus is an aqueous solution, it's always in the form of H3O plus, the hydronium ion. So that would be choice 3. Cl minus, the chloride ion, that is choice 4. And then remember, it's an aqueous solution, so water is usually in excess in aqueous solutions, so that would also be a major species. HCl is not going to be a major species because, again, HCl is a strong acid. It's completely dissociated. And OH minus, although there actually is some OH minus concentration in this solution, because it's an acid, this OH concentration is very, very small. So you can think of that as really non-existent. So what we're left with is 2, 3, and 4. And again, that is choice B. All right. Moving on to titration. An important way to measure the concentration, the unknown concentration of an acid or a base, is through titration. And you probably, if you haven't done this in lab yet, you probably will. And you definitely will do it in classes like equilibrium systems. So what a titration is, it's a volumetric way to determine the concentration of an unknown substance. And in this case, we're going to be talking about acids or bases. And what you do is you use a standard solution. So you have a standard of known concentration. This is called the titrant. And you add this slowly. You keep careful measure of how much you add to your unknown solution. And then there's a certain point where called the equivalence point, and in our case for acid-base chemistry, the equivalence point would be where the moles of acid and the moles of base equal each other. In general terms, it can be whatever is reacting. The two moles of the 2 moles of reactant equal. And there's another term called the endpoint. Now this is where the indicator, whatever indicator you're using, in acid-base chemistry, it's usually something that changes color. And the endpoint is when this indicator changes color. Now we're assuming that the endpoint is the same as the equivalence point. But that might not always be the case, especially if you go over your equivalence point, as is pointed out on the title slide. Okay, so if we look at a figure of what a titration looks like, if we had a reaction of sulfuric acid and sodium hydroxide, shown up here, we'll have let's say a sulfuric acid solution of unknown concentration. The titrant would be sodium hydroxide, and that's in the burette lines on it, so you can see what volume you're adding precisely. Your
endpoint is reached. You get a color change shown here, slight pink color. Now let's see, how do you actually determine a concentration of your unknown sulfuric acid? Well, when you do your titration, you will get a volume of your titrant that's used. So in the example, your titrant was sodium hydroxide, NaOH. Now, you take this volume and you multiply it by the concentration of your titrant. And this is also known. Your titrant is a standard. So you know the volume because you measure it, and you know the concentration because it's a standard. So you use those numbers to find the moles of your titrant. And this is where it becomes important to use the chemical equation shown here. Now if you notice, for every 1 mole of sulfuric acid, you need 2 moles of sodium hydroxide to react with it. Because at the equivalence point, the number of moles of sulfuric acid is equal to the number of moles of sodium hydroxide times 1/2. Usually, this is a very important step. But a lot of times what you'll have is like HCl and NaOH. Well, HCl has 1 hydrogen, and the mole ratio would be 1:1 then. So if you skip this step with HCl and NaOH, it doesn't matter. But for an acid like sulfuric acid, this is a crucial step. Okay, so after you multiply the moles of NaOH by the factor of 1/2, get the moles of sulfuric acid. Now usually you're looking for a concentration when you do a titration. So you take the moles of sulfuric acid and you divide that by the volume, which you know, and that gives you the concentration. Another way to think of this is the M1V1 equals M2V2 method, that equation. You can think of it as M acid, V acid equals M base times V base. In this case, times 1/2. So let's try a practice titration. If you have 30.34 mils of 0.135 molar hydrochloric acid, and you use that to neutralize 25 mils of NaOH, what is the concentration of the NaOH solution? So take a few minutes and then I'll go through this. Okay. So the best thing to do for a question like this, a word question, where you're not given the chemical equation, the best thing to start with is writing the chemical equation. So if we do the molecular equation, we'd have HCl plus NaOH
goes to NaCl plus H2O. And if you look through that, the number of moles of hydrogen on this side equals the number of moles of hydrogen on the product side is 2. The number of moles of hydrogen on the reactant side is 2. Oxygen, there's 1 on the reactant side. Chlorine is 1 on both sides. Sodium is 1 on both sides. So this is a balanced equation. Remember, you can also write this as an ionic equation, H plus Cl minus plus NaOH, Na plus OH minus going to Na plus Cl minus plus H2O. And remember, these are technically aqueous. So this would be the total ionic equation. And then the net ionic equation, if you remember, you cancel the spectator ions. The important reason that you do this, though, is you want to see the mole ratio. So here we have 1 mole of HCl reacts with 1 mole of NaOH. So it's a 1-to-1 ratio. And at the equivalence point, the moles of HCl will equal the moles of NaOH. Now we use our trusty equation M1V1 equals M2V2. And if you think of 1 being the acid, 2 would be the base. You want to rearrange these equations. What we're looking for is the molarity of the base, and that would equal M1 V1 over V2. And we're given M1 and V1, and we're also given V2. So we simply plug those in. And what we get as an answer would be 0.164 molar. Okay. Let's try a little bit trickier one. What concentration of sulfuric acid, what is the concentration of sulfuric acid if 15 milliliters of it reacts with 18.45 milliliters of a 0.0973 molar NaOH solution? If you remember a couple slides back, it shows the chemical equation for this. If you don't remember that equation, you write it out. Sulfuric acid is H2SO4, sodium hydroxide, NaOH. What you get would be sodium sulfate, NaSO4. But remember, sodium has a +1 charge, sulfate has a -2 charge. So you'll need 2 moles of sodium to balance out that charge. And the combination of the other 2 counter ions would be H2O. That's where our neutralization comes in. Now if we look, you have 2 moles of sodium on this side. We're going to need 2 moles of sodium on this side. Okay, adding that, now we'll have 2 moles oxygen here. We're going to need to add 2 moles of H2O on the product side. Now this should be a balanced equation. And the reason we write that equation now is to see that 1 mole of H2SO4 needs to react with 2 moles of NaOH. So at the equivalence point, the number of moles of NaOH will be 2 times the amount of moles of H2SO4. So now if we want to do the calculation with M1V1 equals M2V2, you can actually, at this point, if you wanted to put in the factor of 1/2, you could. I don't prefer doing that. I like to save that for the end, but it's up to you. It would be equivalent either way. So let's rearrange this equation to solve for M1, the concentration of the acid. M1 equals M2V2 over V1. And we're given M2, we're given V2, and we're given V1. So M1 would be 0.119 molar if you simply plug in the numbers. But you have to remember that that would be for the H plus concentration. And H2SO4 has 2 H's in it. So we're going to have to add that mole factor. H2SO4 has 2 H pluses, or you can think of it in terms of moles of H2SO4 to moles of NaOH. So the final answer would be 0.06 moles of H2SO4. Now this question could also be a little trickier, and it could ask you for what is the hydronium ion concentration or the H plus ion concentration. And that would be this answer. But the question's asking for the concentration of sulfuric acid, so you have to use the mole ratio. Okay, the practice question 8. Now this is a little bit more conceptual. So take a couple minutes and try to answer this question. All right. To answer this question, you really don't need to use any equations. If you remember if you look at the titration curve here, the x-axis is the volume of base that's added. So if you have the same acid solution and you're changing the concentration of the base, you're doubling the concentration of the base, you can just think of that as, well, I would need less of that base. I would need half as much of that base to reach equivalence with the acid. If you can't think of it in those terms, just use the equations. M1V1 equals M2V2. Remember, M1 will be the acid. M2 can represent the base. So if M2 is representing 0.011 molar, we can also write a different equation, M1V1 equals 2 times M2 now, because the second concentration is twice as much, 2 M2 times V3, a third volume. Now what would that V3 be? It would be half as much. Because if we solve, V3 equals M1 V1 over 2M2. V2 is M1 V1 over M2. So you see that V3 is actually equal to 1/2 of V2. Now what choice shows that? That is choice A. If you call this 1, this would be approximately 1/2 to reach the equivalence point. So that's a way you can use these titration type questions in more of a conceptual manner.